Hi, I am Dr. Abhishek Joshi, and in this video lecture we are going to discuss about the power coupling from the LED to the fiber, and will be subsequently discussing about the introduction to the photodetectors. Now let's start. So the content for this video lecture is the power coupling calculation, then the power launching versus the wavelength we are going to discuss, then the equilibrium numerical aperture, and it will be headed with the photodetector. We will introduce the working and the introduction to the photodetectors, as well as the principle, the physical principle of the photodetector, that how it works. So let's start with a power coupling calculation. That's our first topic. So to calculate the maximum optical power coupled into the fiber, consider the case shown in the figure. As we can see in this figure, here we have the source of the light, that is maybe LED or the laser, which we have discussed in our previous lectures. So it is generating the optical light or the intensity. Now this optical distribution, intensity distribution, we can see it is here. Now we know that we are having the acceptance cone of the fiber. So if we have the acceptance cone shown by this, so we can see the overlapping region. So overlapping region of the intensity distribution and the acceptance cone is this much only. So this means only the overlapping region part will be participate in the propagation of light, and the remaining part will be lost in form of radiation. So this is the lost power and this one is the lost power. Only the overlapping region will be participating in the propagation of light. So let's continue. So for a symmetric source of brightness, we are considering the brightness by B, and it is given by AS and omega S, where AS is the area on which the light is generated and omega S is a solid emission angle of the source. So here the fiber end is centered over the emitting surface of the source and is positioned as close to it as possible. So the coupled power can be found using the relation. We can find that how much power is coupled. So if we have the source power given by PS, then the power coupled to the fiber will be PF. Then how much power is generated by the source, it may be LED or the laser, will be PS, and power coupled to the fiber is P of F. And we want to couple the power from the source to the core of the fiber. So the coupled power we are having PF. Now we have to find PF. Now the area of the fiber, we have to consider the area of the fiber, that is A of F, and the solid emission angle. The solid emission angle is given by, this is for the source, so it is omega F, and the brightness is the function of the area of the source, that is AS, and the solid emission angle, that is omega S, integrating with respect to the solid emission angle, that is d of omega S, with respect to the area of the source, that is DAS. So we have to cover the area of the fiber. So area of the fiber is nothing but it is a circle. Now we can find the area of the circle if we consider the center, that is having the 0, and the maximum radius is Rm. Let's take this as Rm. So radius is varying from 0 to Rm, while the angle, so we have to cover the complete circle. So for covering the complete circle, the angle will vary from 0 degree to 2 pi or 360 degree. So we have to integrate for the radius, that is from 0 to Rm, and then we have to integrate to cover the entire circle. We have to cover, that is from 0 to 2 pi. Then for the area of the source, again we have to take the circle, that is from 0 to 2 pi, and the distribution of the brightness, that is from 0 to theta naught, and we have the brightness as a function of theta and phi, where theta is the elevation angle and phi is azimuth angle. Now for a spherical coordinate system, we are having r, theta and phi. So sin theta, d theta d phi and d theta s, and radius is given by r dr. So where the area and the solid acceptance angle of the fiber defines the limit of the integrals. So first the radiance, so radiance is given by the function of theta and phi from the individual radiating point source on the emitting surface. So is integrated over the solid acceptance angle of the fiber. So let's get look on this figure. This figure shows the schematic diagram of an optical source coupled to an optical fiber. That is, the light outside the acceptance angle is lost. As we can see, this power is completely lost and this power is completely lost in form of radiation. So the total power coupled is then determined by summing up the contributions from each individual emitting point source of an incremental area that is given by d theta s and the radius r dr. So it's thus integrating over the emitting area. So for the calculation of power coupled, it is integration from 0 to rs, 0 to 2 pi b naught, integration from 0 to theta naught, cos of theta, sin of theta, d theta, and d theta s r dr. So integration will result as pi b naught integration from 0 to r, integration from 0 to 2 pi sin square theta max d theta r dr. So we are having pi b naught, that is integration from 0 to rs, integration from 0 to 2 pi, and the numerical aperture d theta as r dr. So for the power that is coupled from the source, that is the LED, to the step index fiber. So a step index fiber is having the profile of the index, that's why we're calling it is that as a step index fiber with respect to radius, and the refractive index profile with respect to radius. So this is the profile for the step index. So it is given by pi square rs square b naught numerical aperture whole square, and that is approximately equals to 2 pi square rs square b naught n1 square delta. So the total optical power from the LED, that how much power will be emitted from a LED source. So it is given by PS, that is equals to AS, integrating from 0 to 2 pi and integrating the phi from 0 to pi by 2, that is 0 to 90 degrees. So beta, we have the brightness, and 0 and phi, theta and phi, and sin theta, d theta, d phi. So for the source, that is the LED. So LED here we are taking, considering the LED to the step index fiber. So power emitted is PS pi r square 2 pi b naught, integrating from 0 to pi by 2, that is 90 degree, cos theta, sin theta, d theta. So that is equals to pi square rs square b naught. So we are getting the power coupled from the LED to the step index fiber. It is given by PS, the power of from the source, numerical aperture whole square, and the radius rs is less than equals to a. So we are having the power coupled from LED to the step index fiber given by a by rs square whole square, and the power from the source PS, numerical aperture whole square, if the radius is greater than the radius of the core, that is the A. So A is the radius of core. So let's solve this numerical for the power coupling from LED to the step index fiber. Let's consider an LED that has a circular emitting area of radius 35 micrometers and a Lambatian emission pattern with a power. So power is given, that is 150 watts per square centimeters, and axial radiance at a given drive current. So let's compare the optical power coupled into the two-step index fiber, one of which has a core radius of 25 micrometers. So core radius A, small a is given to us, that is 25 micrometers, with a numerical aperture. So numerical aperture is given by 0.2, and the other which has the core radius, so second one, so we can take it as A1, second one is A2, the radius of the core. There are two fibers and it is given by 50 micrometers. With a numerical aperture, again the numerical aperture is same, that is 0.2. So for the larger core fiber, we are using the expression, that is power coupled from LED to the step index fiber is given by PS numerical aperture whole square pi square RS square B naught numerical aperture whole square. Now we have the values of the numerical aperture, that is 0.2, we are substituting it here. We have the value of the brightness B naught, that is given by 150. So this is B naught, that is 150 watts per square centimeter, and RS, the value of RS we have, that is 35 micrometer, and that is the emitting area. So it is given by 0.725 milliwatts. So we are getting the power coupled from the source, that is LED, to the fiber is 0.725 milliwatts, and we can see that we have given the power of 150 watts. Okay. Now if we consider the second case, that the fiber end face with a smaller dia, we can see for the power coupled from the LED to the step index fiber, that is from 25 microwatts and 35 micrometer whole square, and PS taking the ratio, and numerical aperture whole square. So if we are substituting the values, that is 25 microwatt and 35 microwatts, and the power which we have calculated, that is how much power is coupled. So we can get the power coupled from the LED to the step index fiber is 0.37 milliwatts. So let's discuss the power coupled from LED to step index fiber mathematically. So in the case of a graded index fiber, the numerical aperture depends on the radius r from the fiber axis through the relationship defined by the equation, this equation. So thus for the equation A and B, the power coupled from the source emitting LED into the graded index fiber becomes, that is RS is less than A. So from this LED to graded index, it is 2 pi square B naught, and the integration is from 0 to RS n square R minus n2 square R dr. So further simplifying this expression, so we know the relation, that is, and this is given by, for the fiber graded index fiber, we have the parameter alpha. So it is given by 2 pi square RS square B naught n1 square delta 1 minus 2 by alpha plus 2 RS by the radius of the core A and raised to power alpha. So alpha is the refractive index profile parameter. So this is refractive index profile parameter. So where the last expression was obtained from the equation, so we can get, for the simplifying it, we can write this expression as the power of the source, that is PS, that is pi square RS square B naught n1 remaining terms is as it is, that is 1 minus 2 by alpha plus 2 Rs by A whole raised to power alpha. So these analysis assumed perfect coupling conditions between the source and the fiber. So this can be achieved only if the refractive index of the medium separating the source and the fiber and matches the index, that is N1 of the fiber core. So if the refractive index N of the medium is different from N1, then for a particular fiber and phase, the power coupled into the fiber reduces by the factor that is given by R, and it is, we can find R, that is N1 minus N by N1 plus N whole square, where R is the Fresnel's reflection or the reflectivity at the fiber core and phase. And the ratio, that ratio is a small r, that is N1 minus N by N1 plus N, is known as the reflection coefficient, relates the amplitude of the reflected wave to the amplitude of the incident wave. So let's discuss the power coupled from LED to the graded index fiber. So for the graded index fiber, the numerical aperture depends on the distance r from the fiber axis, and the power coupled from the surface emitting LED into the graded index fiber becomes Rs, that is less than the radius of the core. So we can find the power coupled from LED to the graded index fiber, that is P LED comma graded, that is 2 pi square B naught. B naught is the brightness or the maximum brightness, or you can say the maximum brightness, integration from the radius, that is 0 to Rs, N square R minus N2 square RdR. So we know that the graded index profile, it's having the constant cladding, and the core refractive index profile is changing. If it is parabolic, then alpha will be equal to 2. If it is a triangular profile, then alpha is equals to 1. If alpha becomes infinite, then it will become the step index profile. This we have already discussed in my previous lecture. So we have 2 pi square Rs square B naught N1 square delta 1 minus 2 by alpha plus 2 Rs by A raised to power alpha. So we get the power coupled from LED to the graded index fiber, that is 2 ps N1 square delta 1 minus 2 by alpha plus 2 Rs by A raised to power alpha. So the power launching versus the wavelength. So what is the relation between the power launching, means how much power will be launched, and the wavelength? So the optical power launched into a fiber does not depend on the wavelength of the source, but only on the brightness, that is its radiance. So number of the mode propagated in a multi-mode graded index fiber of core size A and the index profile, that is alpha, is given by, so what we have, we are having number of modes, that is given by m, that is equals to alpha by alpha plus 2 and 2 pi a n1 by lambda whole square delta. So the radiated power per mode, that how much power will be radiated, is given by the source power divided by the how much modes are there inside the exists inside the fiber, that is capital M. So Ps by M from a source at a particular wavelength is given by the radiance multiplied by the square of the particular wavelength. So we are having Ps by M, that is equals to the brightness B naught lambda square. Thus the twice as much of the power is launched in a given mode at 1300 nanometers than the 900 nanometers. So hence two identical sized source operating at different wavelength but have the identical radiance will launch equal amount of optical power. So equilibrium numerical aperture, we know that the numerical aperture of the core is different, numerical aperture of the source is different, even the coupling medium is having some numerical aperture, and the numerical aperture is varying with respect to the length also. So the light source may be supplied with a short, that is 1 to 2 meter of fiber flybed attached to it in order to facilitate the coupling from the source to the system fiber. So to achieve the low coupling loss, the flybed should be connected, have the nominally identical numerical aperture and the core diameter. So a certain amount of optical power is lost at the junction and the exact loss depending on the connecting mechanism on fiber type. Also, an excess power loss will occur in first few tens of meters of the multimode system fiber, and this excess loss is a result of non-propagating modes scattering out of the fiber as a launched mode come to an equilibrium condition. So the excess power loss we are talking about is shown in the figure of the fiber numerical aperture at the input of the fiber, and the light acceptance is described as a launched numerical aperture, that is numerical aperture in. So if a light emitting area of the LED is less than the cross sectional area of the fiber, then it's this point the power coupled into the fiber is given by, that is power of the source, that is PS, numerical aperture whole square for the radius of the source that is less than the radius of the core, and the numerical aperture will be equals to the initial numerical aperture. So when the optical power is measured in long multimode fiber after the launched modes have to come to an equilibrium, the effect of equilibrium numerical aperture, that is an A equilibrium, becomes apparent. So at this point the optical power in fiber scales as, so we can see that initial numerical aperture is 0.35, but with respect to the fiber length, the numerical aperture is decreasing and comes to at equilibrium condition, or you can say the constant value, that is numerical aperture equilibrium, and it decreases from 0.35 to 0.2. So as you can see, the x-axis, that is the fiber length in meters ranging from 0 to 150 of meters. So now next topic we are going to start with is the photodetector. So at the receiver side, to sense the photons or the light, we need some sensor or the transducer that converts the light energy to the electrical signal so that we can process it and we can decode our information. So photodetectors are nothing but a transducer that is used to transform the one form, that is the light energy, to the electrical signals. So the detector is an essential component of the optical fiber communication system and is one of the crucial elements. So its function is to convert the received optical signal into electrical signal, which is then amplified before further processing. So the following criteria we have to keep in mind while designing a photodetector or selecting a photodetector: that what is the size of the photodetector, and the size of the photodetector should be as small as possible. Then the material used for the photodetector, that what material we are using it and what will be the sensitivity of the material at a particular wavelength. Then the high sensitivity at the operating wavelength, fast speed and the short response time to obtain a suitable bandwidth, sufficient bandwidth to handle very high data rate, low cost with high reliability, and the last important point is the minimum noise introduced by the detector. So the noise may be introduced due to the dark current, the leakage current, and the shunt conductance. So shunt conductance must be very low. Now what will be the physical principle of the photodetector? So physical principle means how it works. So we know that in a diode we have p-type and n-type, and between p-type and n-type we are having a junction. Now this junction doesn't allow the free carriers or the majority carriers, that is holes, to pass through it. Similarly, the n-type have the electron and this junction act as a barrier and it will not allow the electron to pass through the junction. But when we apply the reverse bias voltage to it, means P side we are applying with a negative and the N side is applied with a positive voltage. So what we see is there is a breakdown of the junction, and due to this breakdown the electrons and the holes pairs are generated and it will be attracted by the opposite polarity. Here we have the negative polarity, here we have the positive polarity. So it will attract, and we know that the flow of the charge is known as the current. So this is the basic principle working. So the basic detection process is an intrinsic absorption shown in the figure, which you will see, that is a PN photodiode, and this device is a reverse bias and electric field developed across the PN junction sweeps mobile carrier, that is holes and electrons, to their respective majority site, that is p-type and the n-type material, and the depletion region is therefore created on either side of the junction. So the field accelerates minority carrier from both the sides to the opposite direction of the junction, forming the reverse leakage current of the diode. So the photon incident in or near the depletion region of this device, which has an energy greater than or equal to the band gap energy, that is Eg of the material, and we know that according to the Einstein equation, Eg is equals to h nu, or it should be greater than equals to h nu, will excite an electron from the valence band to the conduction band. This process leaves an empty hole in the valence band and known as the photogeneration of an electron hole pair, as shown in the figure. So the carrier pairs so generated near the junction are separated and swept drift under the influence of the electric field to produce a displacement by current in the external circuit in excess of the. So the photogeneration and the separation of the carrier pair in the depletion region of the reverse biased PN junction is illustrated in the figure. So as we can see in the figure, we are having the energy band diagram where there is a hole and the electron, and the valence band and the conduction band, that is HF, that is greater than the band gap energy, that is Eg. And here we have the p side and the n side, then the generation of the electron hole pair, and due to the application of the reverse bias, that is negative and positive, there is a motion of the charge, that is the reverse attracted by the reverse polarity. Electrons will be attracted by positive and the holes will be attracted by the negative. So this is the operation of the PN photodiode, photogeneration of electron hole pair in the intrinsic semiconductor. The structure of the reverse bias we have seen here, and the n-type illustrating in the depletion region. The energy band diagram we can see here for the reverse bias case in a PN junction diode for the photogeneration and subsequent separation of the electron hole pair. So in this lecture, we have discussed about the power coupling calculation, the power launching versus wavelength, the equilibrium numerical aperture, introduction to photodetectors, and the physical principles of the photodetector. So here I am going to stop this lecture. Thank you.